Okay, we're recording. Hello, students. Today I want to provide an introduction to systems of linear equations. The goal in our class is to study the Gauss-Jordan elimination, which will be applicable to all types of systems, different numbers of variables and different numbers of equations. But we want to do some review work with two linear equations and two unknowns and basically remind ourselves of some basic strategies to solve these systems. This work is very important in all levels of mathematics. So what we will do today is basically refresh your memory and maybe give you some new ideas about some of the techniques that you have learned in the past. So let me go ahead and share my screen. Now, when it comes to working with linear equations, we need to do a little bit of review just to remind ourselves of where we have been. And I never find this to be a waste of time for my students. So again, like I said before in the introduction, we want two linear equations and two variables for now. Now, just to review a couple of items from the past, when we define slope for a line, that is, the linear equation and the line are basically equivalent. When we have a linear equation, its graph is a line. That is, the linear equation determines a linear function and line linear. The line came first, then we decided on linear. So when you've got two fixed points in the plane, you define slope. That is, you define a change in y over the change in x, which is really what many of you termed rise over run. So let me just go ahead and write that in, rise over run. So all we have to do is just maintain the order. For instance, it doesn't matter what we start with first. We could do y1 minus y2 as long as we did x1 minus x2. But it's customary to write the fixed points with these subscripts and then just write the change in y over the change in x, starting with this ordered pair. And so we would have y2 minus y1 divided by x2 minus x1. And of course, there are many notations that you can use with this, and feel free to use them. And I also wanted to point out some of the forms that we find useful when we work with linear equations. The first one that you find very helpful is the point slope. So if you basically just cross multiply using the slope equation and exchange the fixed point x2, y2 with the variable point x comma y, then you basically get a linear equation, which we call point slope, because again, you have the point and you have the slope that we've defined here. Another useful form is called the slope intercept, which basically just means that you isolate the y on one side of the equation. And when you collect the constant terms here, you just relabel that constant term as b. Again, that's just a standard notation for the y-intercept. So we call it slope-intercept because this b, obviously, if you let x be 0, this becomes the y-intercept. So this is also a very useful form of the linear equation. Now, though these are very useful when it comes to graphing, usually when we have systems of equations, they're in the form that I've listed here last, called the standard form, which means that all of the variable terms rest on one side of the equation, in this case, the left-hand side, and then all constants are on the right-hand side. So A, B, C are fixed. So we have a standard form that looks like this, which all of these are equivalent to. That is AX plus BY equals C. So when you see a system of equations that are linear, it doesn't necessarily mean that they have to all abide by this form, but you can certainly put the equations into this form. Now, As I've just mentioned here, which I said in the introduction, the graph of a linear equation is a line. So that's really where all of this comes from. We start with this definition of slope to describe the line, and then the linear equation is something that we get for free. Just remember the slope is consistent. So when we think of a line, we think of it as having a consistent slope. There is no curvature like we would see with an exponential curve or a quadratic curve. In this case, for the line, the curvature is zero. So now when we do systems, our equations will have the standard form, but what I've done here is I've written the coefficients and the right-hand sides in terms of a matrix notation, because that's what we will do when we start looking at row operations in the Gauss-Jordan elimination technique. So when we write an equation that has this form, we can often use different coefficients and different right-hand sides using subscripts. And notice I'm not using an x and a y here. I'm using an x1 and an x2. So what we have is x1, x2 are variables. So what's convenient about the subscript notation is that we never run out of variables. We never run out of coefficients. So this is a standard form, and again, it underscores the use of the matrix or the array if you have studied some computer science. And of course, that is a monumental importance when you think about computer programming. So again, here, this will just support what we do as we continue with the topics. Now, we're going to do several examples, and they're very straightforward, but we're going to get plenty of review of basic topics. The first technique that we can use to solve the system of linear equations that we have here is elimination. And elimination tends to be the most popular technique. Substitution is actually a very good technique. We find it maybe more useful when the coefficients are less user-friendly, or we're looking to utilize certain applications with linear equations. And we find that when we use substitution, the technique is much simpler, especially if the form of the equations has one particular variable isolated. So we find substitution can be very simple in certain cases. Even though the elimination tends to be more popular, we usually just choose a method based on what we're trying to do in a specific example. Okay, so let's look at a very simple example. And what I'll do for now, ladies and gentlemen, is I will just use the X and the Y just to make it a little bit easier. Let me adjust the camera here. So one thing that we can do when we solve linear equations is remember, for any equation, we can adjust the equation via multiplication by a constant. That does not change the solution of the system. It simply allows us to reduce the equation and basically to maybe exhibit more user-friendly numbers. Because notice, if we have common factors in this equation, they can just be absorbed by simply multiplying by a given constant. And let me just show you what I mean here to write this a little bit more specifically. We can factorize all of these numbers, especially in the first equation, to exhibit the 3 that's common to all of the terms, and we can factorize here to exhibit the 2 that is common to all of the terms. So let's do that. So we have a 2 times 3x plus, and I'll just put the 1 in for emphasis, 3 times 1 y, you don't have to. And then we have the 3 times 13. And then here we can do the same thing with the 2. 2 times 4x plus 2 times 2y, and then 2 times 23, just simple factorization. So now what we want to do is just showcase the common factors. In the first equation, we have 3's that are common to each term, and in the second equation, we have 2's that are common to each term. Factoring is an important operation in mathematics. We can't do too much of it. I don't think we ever worry about too much practice with factoring. We never get enough of it, actually. So now in the first situation, we can multiply the equation by 1/3. Basically, the 3's absorbed. They just go away. So here, multiply by 1/3, and here multiply by 1/2, and we can do that visually. Now, I also should say here, none of this is required. You would still get the same solution if you didn't do this, but it certainly makes the process simpler when we don't have to worry about additional numbers that are hanging around, basically getting in the way, that are eventually going to factor anyway. So in the first equation, equivalently, again, the 3's go away, so we have 2x plus 1y, or y, equals 13. And then in the second equation, the 2's go away, and we have 4x plus 2y equals 23. Now, what's interesting about this problem is that elimination would be an easy way to solve it. And again, this is completely up to you. With elimination, we want to basically eliminate one of the variables. So we have one equation in one variable. In the worksheet, this is often called the addition method. So that works just as well because you want to add the equations to eliminate a particular variable. So what we can do here, and this is completely your choice, just most simply multiply the first equation by a -2 if we're thinking about eliminating the y terms. But you're thinking that's going to also eliminate the x term. So let's see what we get. So equivalently, here let's multiply by the -2. So the -2 times the 2 is a -4. And then, of course, the -2 times the y, we'll just go ahead and write -2y. That's an equivalent expression. And then, of course, the -2 times the 13 gives us a -26. And then here, of course, we have nothing to do. 4x plus 2y equals 23. Now, it is customary to do this, even though it's not required. We're just going to add the equations, and we see that in both cases, these two terms will absorb because they're additive inverses, and also these two terms will absorb because they're additive inverses. So when we do that, of course, -4x plus 4x is 0, and -2y plus 2y is also 0. And then, of course, the -26 plus the 23 is a -3. So we get the following logical statement. And when we think about logical statements, they have truth values. And so when we see this 0 equals -3, this is what we say as a truth value to be false. So this is a false equation or a false statement. Now, what's good about this particular technique is that all of these steps produce equivalent systems. We can add equations, multiply equations by constants, and of course we can write the equations in different orders, which means an exchange of rows, so to speak, when we think about a matrix. But none of those operations change the system solution. We often refer to those operations by the phrase elementary row operations. So what we see here, when we perform these operations, we get a statement that is false. And so when we look at this, and of course I got to get the lights back on by waving my hands around. What we see in this particular case is that we reduce the system to an equation that is false, a statement that is false. So this implies or is equivalent to no solution. We don't have an ordered pair that will actually satisfy this system. And so when you think about graphs, you would see that the graphs of the particular equations here, even if you look at these, they are parallel. They are parallel. That is, they do not intersect in the plane. But we don't really want to focus on the idea of relying on a graph to tell us whether or not we have a solution because graphs are imperfect. We often do the graph once we understand the systems because the visual effect or impact of the graph can be very intuitive and very informing. So we say no solution, or if you like, we signify the lack of a solution by the symbol for the empty set. That means that the solution set in this case has no elements. So this symbol for the empty set means the set that has no elements. So we'll just say the solution set. This will be helpful when we get to logic. The solution set has no elements. So when we think of a system of equations, not necessarily linear, any types of equations, nonlinear equations are very popular in systems that you find in other areas of mathematics and science. And of course, it's always possible to get no solution. So we see the elimination technique is very, very straightforward. Now, let's look at a system similar to the last one, but we want to also get some experience just sketching some linear equations. And also, once we find a solution, just see what the impact of the solution is for the graphs. Now, what you can see here in this particular example is that we have the same thing going on. Move this over just a little. That is, we have common factors in the equations. Again, not removing them does not change the answer, but removing them does make the process much easier arithmetically. So let's go ahead and do that. Excuse me. So we have a 3 common to all of these terms. So 3 times 3x minus 3 times 1y equals 3 times 8. Again, simple factorization. Let me not write more over here. And then for the second equation, we have the same thing going on, 3's. 3 times 1x plus 3 times 2y, and then 3 times 5. So now we can showcase the fact that we have common 3's. This is not required, but I just want you to get used to this technique. You can obviously do this in your head, but it's always nice to write it down and verify everything. So now again, we're going to multiply the first equation by 1/3 and also the second equation to give us a new system that's easier. So we have 3x minus y equals 8. Again, you put the boxes there so you ignore them. That makes it a little bit difficult at first. And then we're left with a 1x or x plus 2y equals 5. So what I want to do in this particular case is use the second type of technique. You are not required to use either. When you do an example, what you're going to find is that usually one technique presents itself, and that's what you opt to do. But again, don't ever worry that the technique that you're applying is not what someone else is doing. It's what you've decided to do, and when you solve the problem, you make the decisions. So what we're going to do is, since we have a very simple second equation, I'm going to label this 1 and 2 so I can refer to them. So by 2, we're going to just solve for x by transposing the 2y terms. So x equals 5 minus 2y. So we just want to say, okay, this gives us an expression for x. Or we would say that we have now expressed x in terms of y. And so now this implies by 1, if you will, we can now substitute into 1 the expression for x. So this gives us 3 times 5 minus 2y minus y equals 8. So now let's go ahead and reduce this. Distributive law. 3 times 5 is 15. Very simple. 3 times the negative 2y, negative 6y minus y equals 8. So now if you like, we can just combine the y terms. And now we can just transpose. We can take the 7y over and we can bring the 8y over. So we'll have, in this particular case, 15 minus 8 equals 7y. Now, of course, equivalently, the 15 minus the 8 is 7. 7 equals 7y. So now, of course, just like we've done before, the 7's absorb. So we just multiply basically by 1/7, and we get y is equal to 1. Now, one thing that we notice here is that in order to solve the system, we also need the x variable. So this is where you go back and look at all the work and say, well, we have a very simple equation here that we use to start the substitution process. So let me just write over here, we're using substitution. And it doesn't matter, again, like I say, what technique you use. Here, I'm just using substitution to remind you of it. So now we will say, using this implies that x equals 5 minus 2 times 1, or 5 minus 2 equals 3. So now this implies, or equivalently, we have x equal to 3 and y equal to 1 as a unique solution. So what we notice a lot of times when it comes to working on these types of problems is that what we want to notice here is that in the first equation, we had no solution. In this equation, we have a unique solution. So what we know is that the graphs of these particular linear equations intersect at one point. So we go from lines that never intersect, that are parallel, lines that intersect at one point. And then, of course, if we were to have infinitely many solutions, that means the expressions for the lines would actually coincide. That would just mean that they were equivalent. The idea is that lots of times when you work matrix operations, if you've got equivalent equations, then you basically end up with a row of zeros. And that simplifies the solution process. So of course, when we think of graphing a particular line, then we know we have infinitely many solutions because we have two unknowns in one equation. So that means we have a free variable. And we'll say more about that when we talk about the Gauss-Jordan process. But as we have now, we might as well go ahead and just get a picture of this. Notice we want to go back to the very simple equations that we have right here because we're just going to be a little bit lazy. So let's go ahead and do that. So notice by 2, if you like, we have 2y equals negative x plus a 5. And so now if we divide by 2, we can write this in the slope-intercept form. So y equals, in this case, negative 1/2 x plus 5/2. So that gives us a slope-intercept form. Very easy to use. Now, if we look here at number 1, we have, if you will, and we can just rearrange things, you can take the y over and the 8 over. So we have y equals 3x minus 8. That's a slope-intercept form. Now, one thing I impress on students is that you can use the y-intercept as a point. It just depends how convenient it is to use that point. But you can also just, for instance, set a particular value of x and then solve for the y. So there's nothing about any of this that is unique. You simply get a graph, which makes the process really simple. So now let's go ahead and do that. We have a simple y-intercept here that's not too big, just 2.5, and we've got a slope of -1/2. So let's go ahead and draw this picture. So if you will, since we've got all these halves here, we'll just do in half steps. So 1, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves. And do the same thing here. 1 half, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, however many we need. And then we'll do some here. We've got a -8, so I'm going to just go ahead and do that. So we're going to need 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. These are not too huge. So you can either draw your picture really well and use different points, or and then when you actually intersect the y-axis, you actually get what's very close to -8. But what I'm doing here is just saying, okay, we're just going to be a little bit lazy and not have to work too hard using the y-intercepts in both cases. So now notice we need 5 of these. So we've got 1, 2, 3, 4, 5. So that for the first equation is right here, or equation 2, excuse me. So that's the 5 halves. And then we want to go down 1 and to the right by 2. So we go down 1, that brings us here, and to the right by 2. So that'll bring us over here to 4 of these. 1, 2, 3, 4. So we're right here. So notice this point here on the y-axis is 5 halves, and we descend to 3 halves, and we move to the right to 2, because we have -1/2. So now when we look at this, we can say, okay, let's just write this. So we've got 3 halves and a 2. Even though we're getting extra numbers here, you're thinking you've got the solution set, why not just use that? But I want to give us some practice using the slope and the y-intercept just for fun. And now, of course, we had this intersection point, which is 3, 1. So notice I've gone to the 6 halves, so that's the 3, and then the 1, which is right here. So the picture's not horrible. We get a good graph. So let's go ahead and connect these. Now, just for precision, that's our intersection point, which is 3, 1. And I'm not going to write that in yet. I'm going to go ahead and draw the other graph. Now, we can be lazy, or we can get a new point, or just say that's a point on the line, which is 3, 1, because it's common to both. And then, of course, we have the -8, which is down here at -16 halves, right here. So this is -8, which is, again, -16 halves. So we can just now connect these lines, or connect these points. So now we can mark this in as 3, 1. So that's kind of a simple way to get graphs. And I've done some extra work using the slope definition just to give us some practice. But of course, you can do this in many different ways. So now we can just label this. So this is y equals 3x minus 8. So we know that has increasing because, again, the slope is positive. And the other one is decreasing because it has a negative slope, as we see negative 1/2. So this is y equals negative 1/2 x plus 5/2. And I'm getting close to the 5/2 here, which is the actual y-intercept for this equation. So lots of times when you're working in finite mathematics or economics, business, or whatever, you want a picture of things. But notice the picture is a byproduct of the algebraic work that you've done. You don't want to use the picture as a means to determine things. That's really backwards. So once we understand the equations, we understand the functions, how they're related, then we could draw the picture based upon all of the ideas that we have confirmed. So this picture here just simply represents what we've written out in the problem. So again, though this is review, it never hurts to go back over it and just to give us a nice visual of what's going on. Okay? Now what I wanted to do, before we look at just some simple examples, is to look at another system and exercise the ability to rewrite the system. Now, like I said before, if we have certain things about the system that we find to be overdone, as what I mean by we have additional factors in each term that are consistent, we can absorb them, so to speak. We can multiply by the reciprocal of that number to basically eradicate them. That is, to convert those particular numbers into the one. That is, multiplying an equation by a constant does not change the equation. It does not alter the equation when we are considering solutions. And we can all often do that. It's not a problem. Again, if you just take a single variable and change it, then that's really much different. And so we don't have the luxury there. But as long as each term is adjusted in the uniform manner, we don't change any solution. So what we want to do in this particular case is basically just get rid of the 3's. So in the first case, we can do the same. We can multiply through by 3 to eradicate the 3's in the denominator, and do the same for the second equation, just to make maybe the process a little bit simpler. So let's go ahead and do that. And this is easy to do. If we multiply the 2/3 by 3, the 3's absorb. Now we can do this visually. We just get a 2x plus a 3y. And now, of course, here the 3's absorb, and so we're just left with a -5. And notice I always use absorb instead of cancel because we don't want to think of the number being annihilated, so to speak. I know we use that a lot in differential equations, but I think absorb is a little bit more appropriate, though it may sound a little odd. So now here we multiply by 3, so we get 3x. And now the 3's absorb, and we're left with the -y. And here the 3's absorb, and we're left with the -13. So you can look at this and say, well, that seems a little bit simpler than this equation because it's devoid of the fractions, but it's equivalent. So now if you think about it, we can just go ahead and use the elimination technique, because if we multiply this equation, I know it looks like we're going forwards to go backwards. If we multiply this equation by 3, we don't have to use two different multiplications. The y terms will absorb. So let me just write that out. Multiply by 3. And then, of course, we'll have two terms that are additive inverses. So this gives us equivalently 2x plus 3y equals -5. And then multiplying this by 3, we get 9x minus 3y. And of course, the 3 times the 13 is a 39, so we get a negative 39. Okay? So these are additive inverses. So we will do now the addition. And just note that these absorb. So now, of course, we get a 0 here, but the 2 plus the 9 is 11x plus 0. And notice here we get the negative 5 plus the negative 39, which gives us a negative 44. But of course, negative 44 is negative. Well, let me do one more step. Well, no, this is okay. I'll go ahead and write this out. I'll go ahead and do it this way. This will be 11 times a negative 4. So, of course, 0 plus 11x is 11x. And now I'm going to do the negative 4 first, and then times the 11. So now, of course, the 11's absorb. This is really all we do when we solve equations. We're simply using these axioms that allow us to preserve the system solution. Again, we do it even with singular equations. It's a common technique that we don't even think about. We don't even process it. We just do it naturally. So now, of course, the 11's absorb, and x is equal to negative 4. So we're seeing this elimination technique is very powerful. Now, of course, we didn't use substitution, so we don't have an equation that's readily solved for y, but we can look at these, call this 1 and call this 2. So we'll say by 2, well, conserve the electricity. So now we can solve for this. So again, take the y over, take the negative 13 over. So y is equal to 3x plus a 13. So again, just mentally take the y over, so it's on a side by itself, positive y, and take the negative 13 over, changing the sign, 3x plus 13. So now we have y equals 3 times a negative 4 plus a 13. But of course, 3 times the negative 4 is a negative 12. Very user-friendly numbers, which gives us 1. So y equals 1. So we have, again, a unique solution, negative 4, 1. That will be our unique solution. Okay? So when we think about the elimination process or substitution process, we often let the problem dictate what we need to do. What is easier? What makes more sense? And as you take more math, you take more business courses, even science courses, you will be presented with that. Now, I wanted to look at an example from economics, and I just wrote this out just to make some interesting points. When it comes to supply and demand, again, these are not overly complicated topics, but in this particular case, these equations are written in linear fashion. So when we have what we call a supply equation, we have a price P and a quantity Q. So what you can see here, and I've written just derivatives here, but you don't need to know that. We have a positive slope for the supply equation, so we're going to have an increasing function when we think about the price that is involved with the supply equation, where the Q, the quantity, is the independent variable and the price is the dependent variable. So basically we see here, if supply increases, so does price. Now for the demand, we have a negative slope here. So we would think of this as a decreasing function. And of course, I've written the negative 1.2 is what, negative 6/5. just rewriting the 0.2 as 1/5 and creating fractions here instead of the decimals. And of course, 0.8 being replaced with 4/5. So now what we would see is that if the demand were to increase, the price would decrease and vice versa. So again, just like the two equations that we graphed, one had an increasing slope, so to speak. Well, we'll just say the line produced an increasing function. Okay, so we don't necessarily say increasing slope, we say positive slope. So as the independent variable gets larger, so does the dependent variable. So in this case, in the demand case, we have just the opposite of that. We have a negative slope. So the increase and decrease are opposed, so to speak. As one variable gets larger, the other variable necessarily gets smaller. So again, there's more to be said with this, and you'll be able to do that in your economics class. So the supply equation here, we have price is equal to 4/5 times the quantity plus 13 over 5, just writing 2.6 as 13 over 5.6 being 3/5, and then rewriting the improper fraction. As you see, I've done the arithmetic here just to let you know what I'm doing. And then, of course, for the demand equation, we have P equals negative 6/5 Q plus 9. So we simply rewrote these. We didn't bother to do any more than that. Now, why did I leave these equations this way? Because this is basically dictated by what the problem is asking us to do. We have a term or a phrase called market equilibrium when the supply is actually equal to the demand. So we would want to know what is the price and also what is the quantity that corresponds to, in this particular case, market equilibrium. So that would mean that we would want to set, the two equations equal. That is, when we look at this, we've got P solved in each case. So we can definitely just set both equations equal because they've been actually solved for P. So by leaving the equations as they were written initially, except for converting the decimals to fractions, we actually help ourselves solve this problem. So now we've got 4/5 Q plus 13 over 5, as you see here, equals to negative 6/5 Q plus 9. And now at this point, we're like, okay, we can easily solve this. We have one equation, one unknown. So what I've done here is I've added the 6 to the 4 to get 10 over 5Q. And then we've got what, 9 minus the 13 over 5. Well, just to make this a little bit simpler, now I've just decided to go ahead and eradicate the 5, though it's not required. It makes the arithmetic a little easier. So multiply the entire equation by 5. The 5's absorbed here to give us 10Q. 9 times 5 is 45. And of course, multiplying the negative 13/5 by the 5's absorbed, and we are left with negative 13. But of course, 45 minus 13 is 32. So now when we look at this, we just divide by 10. Q is equal to 32 over 10, but of course we can factorize the 32 as 2 times 16, and the 10 is 2 times 5. So you see that the 2's absorb. So this gives us 16 over 5, which is 3 1/5. Now, of course, when you look at that, you're thinking, okay, well, that's not 1 unit. It's between 3 and 4, a little bit closer to 3. But again, we have to follow the mathematics and just say, okay, when we get closer to 3 units produced, the quantity, then we're close to market equilibrium. So there's no way to exactly hit it because this is not an integer, but that's okay. That's just exactly what the definition asks us to do, and we have supplied that. Now we're thinking, okay, substitution says that we have the value for Q, we just need a value for P, but that's really easy. I just chose this equation here. We've already solved explicitly for P by the way the equations were introduced to us, so we don't have any work to do. So we have 4/5 times 16 over 5 plus 13/5. Again, this equation, and if you like, you can call this 1 and call this 2, and you can just say by 1. So now this gives us a 4 times a 16, which is 64, and 5 times 5, nice perfect squares, we've got 25. And so now for a common denominator, multiply and divide by 5. So we have 13 times 5 and 5 times 5, which gives us 65 over 25. Now we add these two, 64 and 65, to get 129. And of course, division, 5 times 25 is 125. So we've got 4 extra, so to speak, a remainder of 4. So this gives us 5 and 4 over 25. So it's easy to actually convert this to the decimal 0.16. We could just simply do some division, or we can just write 4 over 25 as 2 over 5 quantity squared. But of course, 2 over 5 is 0.4. You square it, you get 0.16. So probably easier to think of it that way. So now what we see for market equilibrium, we have a quantity of 3 1/5 units, and we have a price of $5.16. So you don't, when you're just solving systems of equations that have no particular bearing on a particular problem, then you can choose whatever technique you want. But we see here that we want to take advantage of the fact that the equations came in this nice form. So that's where the substitution is the best method of solution. So like I said before, you simply have to look at the problem, especially if it's an application of the techniques that you've learned, and then decide which method is best. Also, as you work other types of problems, do not worry about what the numbers are. Simply apply the basic theory. If you need to find a slope, you have the equation for slope. You can simply write down equations based on your basic theoretical understanding of lines. And then from that point on, you can simply use the substitution technique or the elimination technique. If a particular technique doesn't seem better than the other, then you just make a selection. So hopefully what we've seen here with this technique is that now we have a good review of some of the mathematics that we learned in our previous algebra classes. And I think as you find, if you practice with this, then as we get more into the Gauss-Jordan process, that particular process will make more sense, because we'll be thinking, okay, multiplying an equation by a constant, adding equations, exchanging order, changing the order, does not impact the solution. So we will think of those when we define the elementary row operations, and there's really nothing new. So what we're going to find later on is that the Gauss-Jordan technique just simply makes the process of solving systems of linear equations much more efficient, because when you're dragging all these variables around, that gets a bit tedious when the number of equations gets large, and plus the number of variables expands. So we need a much more efficient method. And of course, this method is known worldwide, and it is the cornerstone of many great mathematics and theoretical ideas that you will see as you continue to study more mathematics. Okay, I hope the review has been helpful, and we are done. Thank you.